Now listen. Let A be a normal operator. Consider this remark. Let A is a normal operator on H. A is in BLS such that A star equals A star E. A is a normal operator on H. Then the zero space of A minus Ki. Zero space of A minus Ki is same as zero space of A star minus K bar for all K presents in zero space of A minus Ki is same as zero space of A star minus K bar. How to prove? So the proof is A is normal. A is normal. Then A minus K is also normal. Okay. A minus K is normal. A is normal, then A minus K is normal. A is normal also implies norm A equals norm A star or norm A star equals norm. Norm A star equals norm. Therefore, norm A minus K of x. Norm A minus K of x equals, since A is normal, norm A star is norm A is norm A star. So A minus K is normal, norm A minus K of x is same as norm A minus K star of x. Norm S minus K star of x means it is norm A star minus K bar I of x. Okay, for all x. For all x. So norm A minus, here we see that norm A minus K of x is norm A star minus K of x. Thus, A minus K of x equals 0. This implies and is implied by A star minus K bar I of x equals 0. Okay, A minus K of x equals 0 if and only if A star minus K bar I of x equals 0. A minus K of x equals 0 means x of all in the x of all in set of A minus K I. Okay, if and only if A star minus K bar I of x equals 0 means x of all in 0 space of A star minus K bar. So this is what we require here. So the 0 space of A minus K is same as 0 space of A star minus K bar I. This happens only when this A is normal. That is the crucial point here. When A is normal, then 0 space of A minus K is same as 0 space of A star minus K bar I. Enough. Now, let Ax1, now we are going to another interesting result. Let Ax1 equals K1x1. A is a normal operator. And Ax1 equals K1x1. A2x2 equals K2x2. A1x1 equals K1x1 and A2 of x2 equals K2x2. Without K1 and K2 are differs. K1 differs from K2. Moreover, if this x1 and x2 are non-zeros, then clearly set x1 and x2, set x1 and x2 are linearly independent. Linearly independent. If A is in BLH, what is A? A is in BLH. A is in BLH and A is a normal operator on H. Then, if Ax1 equals K1x1, Ax1 equals K1x1 and Ax2 equals K2x2, Ax1 equals K1x1, Ax2 equals K2x2, with K1 and K2 are differs. If x1 and x2 are non-zero eigenvectors corresponding to this eigenvalues K1 and K2, if x1 and x2 they are non-zero eigenvectors corresponding to this K1 and K2, corresponding to this distinct eigenvalues K1 and K2, then this set of x1, x2 are linearly, the set x1, x2 is linearly independent. Set x1, x2, which is linearly independent. How to prove? Such proof is immediate. If there exists lambda 1 and lambda 2 such that lambda 1 x1 plus lambda 2 x2 equals 0 for the linearly independence, consider this lambda 1 x1 plus lambda 2 x2 equals 0. Now we have to show that this lambda 1 and lambda 2 are zeros. With the lambda 1 and lambda 2 following k, they are scalars. Now consider k1 lambda 1 x1. K1 lambda 1 x1. K1 lambda 1 x1. What is K1 x1? This is equals lambda 1 into K1 x1. K1 lambda 1 x1 is lambda 1 into K1 x1. This equals lambda 1 into K1 x1 means it is A x1. But it is linear. So this is A of lambda 1 x1. Okay. That means K1 lambda 1 x1 equals A lambda 1 x1. But from here, what is lambda 1 x1? Lambda 1 x1, from there, lambda 1 x1 equals minus lambda 2 x2 from here. Okay. So this equals A minus lambda 2 x2. A minus lambda 2 x2 equals A is linear minus lambda 2 into Ax2. Why? Because A is linear. But what is Ax2? Ax2 equals K2x2. Okay. Minus lambda 2 A lambda 1 x1, that is A of minus lambda 2 x2 equals minus lambda 2 k2 x2 minus lambda 2 k2 x2. Okay. Equals minus lambda 2 into, minus k2 into lambda 2 x2. Okay. But what is lambda 2 x2? It is minus lambda 1 x1 equals minus k2 into minus lambda 1 x1. That equals k2 lambda 1 x1. So k1 lambda 1 x equals k2 lambda 1 x1. Finally it is k1 lambda 1 x1 equals k2 lambda 1 x1. So that means k1 minus k2 into lambda 1 x1 equals 0. k1 minus k2 into lambda 1 x1 equals 0. That happens since k1 differs from k2, k1 and k2 are differs, then clearly k1 and k2 are differs, clearly lambda 1 equals 0. Why? Because x1 is also non-zero. Lambda 1 equals 0. Similarly, we have to show that this lambda 2 also 0. By the same argument, we can also show that lambda 2 equals 0. Lambda 1 and lambda 2 equals 0. So for this linear combination, lambda 1 x1 plus lambda 2 x2 equals 0 implies lambda 1 and lambda 2 are 0, means the set x1 x2 is linearly independent. Okay. Now we are going to an important definition. That is, consider K. K equals inner product Axx. K is any scalar. K equals inner product Ax x1 for all x of following H with the norm x equals 1. Consider this scalar quantity. K equals inner product Ax x for x of following H with the norm x equals 1. So this K is called as, it is known as a Rayleigh quotient. This K is known as, it is a Rayleigh quotient. R-A-Y-L-E-I-G-H, Rayleigh quotient. So consider this K K equals set of all, K equals inner product AXX for all x of all in H with the norm x equals 1. So this scalar K is known as Rayleigh quotient. So consider the set of the Rayleigh quotient of A with respect to X. K equals inner product AXX for all x of all in H with the norm x equals 1 is called the Rayleigh quotient of A with respect to X, or Rayleigh quotient of A at X. Okay. Then the set of all such Rayleigh quotients, inner product AXX for all x of all in H with the norm x equals 1. That is, the set of all these Rayleigh quotients is known as the numerical range of E. That is denoted as WE. So this is always a constant. K, that is a scalar quantity. The scalar K equals inner product AXX for x of all in H with the norm x equals 1 is known as the Rayleigh quotient of E at X. The set of all these Rayleigh quotients is known as the numerical range of A and is denoted as WE. Clear? Then here we see that this WE, the numerical range of operator A, is always a bounded subset of A. WA is a bounded subset of A. How to prove this one? So far, what is actually this WA? WA equals the supremum of lambda where, or supremum mod lambda where lambda fall in W. Okay. So which is equals supremum set of all modulus of inner product AXX with a x of all in H such that norm x equals 1. But we know that modulus of inner product AXX is less than or equals norm x into norm x. With since norm x equals 1, it is norm x. So it is modulus of inner product AXX which is less than or equals supremum with a norm x equals 1 of norm x that equals norm E. Okay, that means this WA is less than or equals this norm E. Yes. So WA less than or equals norm A. What is WA? That is numerical range of A, always less than or equals norm A, means this WA is a bounded subset of K. Okay. So what is actually the numerical range? Numerical range is the set of all Rayleigh quotient of the operator A at X. So that is the crucial point here. Thank you.